In Chapter 3, we discussed ionic compounds. If you recall, ionic compounds involve metals from the left side of the periodic table bonding with nonmetals from the right side of the periodic table. And what happens is the metals transfer or lose electrons, and they go to the nonmetals, which gain the electrons. In ionic compounds, this transfer of electrons creates charges. The metals losing electrons becomes positive ions or cations. The nonmetals gain electrons, which become negative ions or anions, and those opposite charges attract. Now, when they attract, they don't form molecules or what we would call an individual unit. Instead, they form what we call crystal lattices or crystal arrays. I think of it kind of like as a bunch, but it has a very specific arrangement of the ions. So when we think about covalent compounds, we're going to look a little bit differently. We're going to look and see how they're a little bit different. So just looking right here. So in covalent compounds, instead of transfer of electrons, the electrons are shared. Now, what both ionic and covalent bonds have in common is that the electrons that are shared or transferred for ionic bonds are the valence electrons. Recall, the valence electrons are the electrons in the outermost shell of the atom, so they're the ones on the most outside of the atom. So in covalent compounds, we're going to see these electrons are shared. Another thing that we notice about covalent compounds is it occurs between two nonmetals. Also, if it's a nonmetal and a metalloid, they would tend to make covalent compounds. So if I was drawing just a simple sketch of the periodic table, remember there's a stair-step line somewhere here. On the left-hand side, these are metals. And on the right-hand side, these are nonmetals. A hydrogen, if you recall, is also a nonmetal. And then along this stair-step line, except for aluminum, we have here, these will be the metalloids are. And we reviewed this in an earlier chapter, but just to reconsider it. So a lot of times we can tell or predict the type of bonding we would expect just simply by the elements that are involved. And in this chapter, what you're going to notice is the ones that are involved in covalent compounds are the nonmetals and then some of the metalloids. Okay, remember, the ionic compounds, they involve metals and nonmetals together. But covalent compounds are nonmetals. So we're going to be working with a smaller group of metals for these. Now, when two nonmetals or nonmetals and a metalloid get together, they do form molecules. See right here? They form a molecule, which a molecule is an individual unit that does not contain charge inside of it. So this is what we call when atoms bond together in an individual unit that's uncharged, we call that a molecule. Because they form these individual molecules, one of the things we're going to do in this chapter is learn how to illustrate or draw something called a Lewis diagram that kind of shows how we would, the types of bonding we would expect in these different molecules. So that's kind of an overview of how we think about covalent compounds. We know they're going to share their valence electrons, that the elements will be nonmetals and some metalloids, and that they will form individual molecules, and we're going to kind of learn how to illustrate what that molecule might look like. Now, in this case, when we talk about covalent bonds, what we're talking about is a bond that shares two electrons. So here's an illustration I have here with hydrogen, if you look right here. So a hydrogen atom, which is in group 1A, hydrogen has one valence electron. Recall that on the periodic table for main group elements, remember there are the Roman numerals, we have 1A, 2A, remember, and then it goes 3A all the way up to 8A. And for the main group elements, this number that's in front of the A tells us the number of valence electrons. So hydrogen, being in group 1A, would have 1 valence electron. So here, how it's drawn, there's hydrogen, and it's 1 valence electron. And if I had another hydrogen, it would also have 1 valence electron. And so when hydrogens, if they take each hydrogen brings its 1 valence electrons, we end up with 2 electrons in between. Those 2 electrons being shared between the hydrogens is called a covalent bond. In fact, we just call it a single covalent bond because there's only 1 pair shared. Now, more commonly, instead of drawing the 2 dots, I like to use just a straight line, and that straight line represents 2 electrons. So remember, when we draw single covalent bonds with 1 single line, any covalent bond, single covalent bond, the line represents 2 electrons. Here's another example with fluorine. And you can kind of review it looking here. Now you'll notice fluorine has more dots. Fluorine is over here in a halogen, so it is 7A. So a fluorine atom would have 7 valence electrons. So if you look at here, each fluorine has 7 valence electrons. Well, the fluorine has one side that only has 1. If those fluorine come together and share each with their 1, now in between them they have 2, and that's what we call a single covalent bond. Now when we look at it, here's another example I could draw. If we have hydrogen and it has 1 valence electron, and then we had chlorine, and chlorine is also a halogen, so it would have 7. Do you see here, if I put those 2 together, that could make a bond. So now they would be sharing, each would bring 1, and they share right here those 2 electrons, and that makes it a single covalent bond. Now don't worry quite just yet about how we know. Well, we know how many valence electrons each atom has based on the periodic table. But we're going to learn some tricks to help us learn how to draw the pictures. I just want you to get the idea now when we talk about a single covalent bond that they're sharing each sharing 2 electrons between 2 atoms. Now, when we think about bonds, there's not just single bonds. A single bond would be sharing a single pair. But we can also have double bonds and triple bonds. So a double bond, if a single bond, I'm going to write it here, equals 2 electrons, then if something shared 4 electrons, it would be a double bond. And if it shared 6 electrons, it would be a triple bond. So we can have double, single, and triple bonds. We also can have something that's called a non-bonding electron. And if you look right here, I have some examples. So if you notice around this particular fluorine, for example, do you see how some of the dots here, some of the valence electrons are not in between atoms? They're just sitting on the fluorine. We call those non-bonding. Well, non means not, right? So these are not electrons that aren't in the bonding. So non-bonding electrons, or they're commonly called lone pairs. They're kind of just by themselves. In a little bit, you'll see why they're important. We do need to draw the lone pairs. Now, I have a few examples. Let me erase this color so I can kind of see the examples. I have a couple examples here of of molecules, of the diagrams. Again, don't quite worry about how I got them, but let's look. So here, I used a yellow marker, but I don't really like it. Sorry, so I'm going to change. Here, these right here are single bonds, that you have a single line. Those would be 2 electrons. These here are double bonds. So a double bond has 4 electrons, and so we draw 2 lines. And then on the oxygen, you have lone pairs. In fact, we have 2 of them. On this example, this single line would be a single bond. That's 2 electrons. And then we have a triple bond, there's 3 lines. So a triple bond, each line is 2 electrons, so that's 6 electrons. A double bond is 4 electrons. And then my nitrogen right there, you see right there, I drew a lone pair. So when we're drawing the pictures, on this page, I'm not worried about you knowing how I got the picture, but instead taking a look at the picture and making sure you understand what the lines and stuff mean. So I'm going to erase the green. You can go backwards if you want to look at the green again, but I want you, before you go on, just to kind of look at these diagrams and see if you recognize a double bond, a single bond, the triple bond, and the lone pairs. So when you look at a picture, you know what each thing is representing. Now in the ionic bonding, we mentioned something called the Octet Rule, and the Octet Rule also applies in covalent bonding, and here it is. So octet means 8, right? And if you remember in ionic bonding, the elements that have 8 are the noble gases. And noble gases are very, very stable because they have a full or a complete outer shell, a complete valence shell. And they have 8 valence electrons. That makes it complete. If you look carefully at the periodic table, though, that's true for everybody except helium. And on the top row on the periodic table on my little sketch up here, there's only 2 boxes, and this one right here is helium. So you can only have 2 electrons. But even for helium, that's a complete valence shell. So it makes it very stable. So how does the Octet Rule apply for covalent bonds? You can read it here. It says, in covalent bonding, atoms share electrons, their valence electrons, to attain the electron configuration of the noble gas close to them. So what the Octet Rule in ionic bonding and covalent bonding is saying that atoms are most stable when they look outside, and I act like they're people and they're not, but when outside of their outside shells have 8 valence electrons like the noble gases. So in other words, their valence electron, the valence shell, their outer shell is full. And that makes them most stable. So atoms in covalent bonding, the nonmetals with each other, will share electrons. So when they look out to their valence shell, is how I imagine it, it's completely full, just like the noble gases. So we can look at the periodic table and it helps predict some patterns. Now these patterns aren't rules. They're just things that we can kind of predict and expect. Sometimes the element will not follow this pattern, but as we're learning and beginning to understand it, patterns are always very helpful. So here are some common bonding patterns for the main group elements, and we're using the Octet Rule. Recall that the main group elements are the elements on group 1A through 8A. They're the ones that have the A. So if you're looking here, I've drawn a table, and you'll notice that I don't include group 1A, 2A, or 3A. Well, the reason is groups 1A, 2A, and 3A are metals. And so in covalent bonding, we don't expect metals to share electrons. They're involved in ionic bonding. So we are not going to look at those 3 groups. These guys over here are all nonmetals. And I want to move it over further so I don't feel so cramped. So let's look at the table. First we have the group, and so these are just the groups on the top of the periodic table. And then I have their valence electrons. Now remember, for the main group or representative elements, they're also called, the group number equals the valence electrons. So the valence electrons are what the elements have. That's what they have in their outer shell. So how can we predict the number of bonds? Well, remember, they're trying to get 8 electrons. So if, for example, in group 4A, like carbon, if I already have 4, I would need 4 more to make 8. So what I predict is that carbon will form 4 bonds, right? Because I need 4 more electrons. Well, let's continue with that thought. I'll change color. So nitrogen, for example, is in group 5. That means it has 5 valence electrons, so it already has 5 electrons. Well, to get up to 8, it would need 3 more. So what does nitrogen do? It likes to form 3 electrons. Now, if you keep following this pattern, just think it through with me. If I have 6 valence electrons, like oxygen in group 6A, I would need 2 more electrons to make 8. So things like oxygen like to form 2 bonds. And finally, the halogens, we could pick chlorine or fluorine or bromine, any one we wanted. The halogens all bring 7. They're in group 7A. So to get up to 8, they would only need to share 1. So if you take the number of valence electrons and then you see how many it would need to go up to get 8, that predicts how many bonds, the pattern, what we would normally expect. Now, when we look down here at hydrogen, hydrogen is in group 1A, so it only has 1 valence electron. But hydrogen, if you recall on the periodic table, is on this first period, and there's only 2 possible electrons. This only has an s orbital, so hydrogen can only go up to 2. So instead of going up to 8, hydrogen can only have 1 bond. It can't go up to 8 because, remember, on this first row, there's only room for 2. So hydrogen brings 1 electron, and to get over to this noble gas row, it has to add 1. So let's imagine then, I want you to look at these examples, and I'm not attaching them to anything, I'm just drawing bonds. So carbon, I'm going to write how many bonds I predicted here. So carbon, I predict 1, 2, okay, and I would like to draw this in a different, I'm going to draw these examples right here lower. So carbon, we predict would have 4 bonds. So 1, 2, 3, 4. Now looking at carbon, if I have 4, how many electrons? Remember, each line is 2, so that's 2, 4, 6, 8. So carbon already, just with its 4 bonds, has 8 electrons. So we do not expect, see right here, any lone pairs, because it already has 8, and we're trying to get up to 8. That's the octet rule. Well, nitrogen, if we look right here, we expect 3. So if I drew nitrogen, I'd say 1, 2, 3 bonds. So then I count, that's 2, 4, 6 electrons. Well, 6 electron doesn't get me up to 8. So what I notice then is hydrogen, not only does it tend to form 3 bonds, but it also tends to have 1 lone pair. Remember, the idea is to get up to 8. Now oxygen right here in group 6A likes to form 2 bonds. So if I go oxygen and it had 2 bonds, remember each bond has 2 electrons, that would only be 4 electrons. Now I only predict that oxygen would like 2 bonds, so I'm not going to draw more lines, but that would mean it had to have 2 lone pairs. And if we keep working our way down, like chlorine, which has, here we see 1 bond, so I say chlorine has just 1 bond. Well, that's only 2 electrons. So then to get up to 8, it has 1, 2, 3, 4, 5, 6. Adds 3 lone pairs. Now hydrogen can only have, you can see a single bond here because it can only have 2. Remember that hydrogen can only have a single bond. Remember that, it will help you. So we know that some atoms have bonds and lone pairs, and when we add them up, the total number of bonds and lone pairs should equal 4. That's because 4 represents 8 electrons. Now I'm going to wipe off this table, so if in the future you want to just go back a little bit, you can go back and look at this table. So let me just erase it, so if you want to rewind this, you won't have to rewind it quite as far. So this is the common bonding pattern. So now here I have a few examples, and I've drawn in the bonds. There's no double bonds here or anything. I'm just drawing in single bonds. And what I want you to do is look around the atoms and see if you need any lone pairs. So go ahead and pause the video. Try to see what you think, and then you can start the video again, and I'm going to do the answers right now. So if I'm looking at the table, hydrogens only like single bonds, and that will always be true. So if you see a hydrogen with a single bond, you have that one right. So looking at this first example, all my hydrogens have single bonds. Carbon in group 4A has 4 valence electrons. It has 2, 4, 6, 8 around it. But chlorine has 2, and so now I need to add 3 lone pairs, because that means 2, 4, 6, 8. So looking at the second example right here, all the hydrogens are complete. They don't need any lone pairs. But nitrogen has 2, 4, 6 electrons, so it needs 1 lone pair. That would make 8. And oxygen has 2, 4, so it would need 2 lone pairs, right? 6, 8. Now looking at this last example, the hydrogens are happy with single bonds. Carbon has 1, 2, 3, 4, so that's 8. Looking at the bromines, it has 2, and so it needs 4, 6, 8, 3 lone pairs. And this bromine needs 2, 4, 6, and then it has this one right here, 8. So sometimes, and you'll have a homework question, when it just asks you to put in the lone pairs, remember what you're trying to do is use lone pairs for that particular atom to have a total of 8 electrons around it, except for hydrogen. Remember, hydrogen will always only have a single bond.